student I ever met. He was the first student to do research with me, meaning he had the enviable task of setting up most of the things in the lab, including, I think he worked on the glove box, he worked on getting a schlenk line set up in his hood, he worked on setting up the EPR, and setting up the luminescent radical project that we're working on. So after getting sick and tired of setting things up for me, he then went on to prove that the world of chemistry is indeed a very small world by doing an RU at UW-Madison with the first professor I ever TA'd for, John Berry. And then he went on to do more research that he's going to tell us about today in his talk with Dr. Carter Abney, who was the only other undergrad to take an advanced graduate level organometallics class with me as an undergrad. So the world of chemistry is indeed a very small one, and Wyatt has already seen a fair amount of it, especially when you consider inorganic chemistry. So his interests are many in chemistry. He knows a lot about chemistry at this point as an undergrad, but his primary interests are in synthesis and spectroscopy, and as a true inorganic chemist, all things metal, whether you're discussing chemistry or music. So that is another shared interest of Wyatt's and mine. So after this, he'll be leaving Lawrence and heading over to the beautiful state of Virginia to pursue a PhD in chemistry at the University of Virginia. So with all of that, I'll turn the floor over to him, but please welcome him with me.
Thank you, Graham, for the introduction. Thank you all for being here on this kind of hooray Friday. I'm very excited to share with you the work I did this past fall at Oak Ridge National Lab. And to most of you, you've heard bits and pieces, but now you're trapped here and can hear all of it. So as my title suggests, I'm going to be talking about making this new type of carbon monoxide oxidation catalyst made from these metal organic frameworks, which is a lot of words and very jargon-full. So we're going to start by unpacking that and talking about what metal organic frameworks, or what MOFs are for short. What we have here is we're building up to these more complex 3D structures from very simple building blocks. So we have this blue line and this red sphere, and they're coming together to make this cube, which is going to be repeated out in this crystalline pattern. Fantastic, and peeling away a layer of chemistry. This blue line is an organic linker. The red sphere is a metal unit, a metal cluster. So that's where we get our metal and organic. And the framework is putting it all together. So what's so fantastic about these MOFs is we can swap out a metal and change the properties of our MOF. It's very plug and play. We can do the same thing with the linking unit, and we have now new applications or a different MOF, different structure. What I'm more interested in is adding a secondary linking unit and tuning the ratio of those two to fine-tune the properties we see in this final MOF product. That's the ultimate goal of the synthesis, and before we get into that, we're going to talk about why people care about MOFs and why they're suddenly, about 2 decades ago, burst onto the scene. And a lot of this arises from their porosity. We can see here is a more complex structure than that simple cube. And behind it, we have this green sphere and this orange sphere. Those are kind of modeling the pore size and the channels running through this MOF. And what you can see is they're rather large. And to give some context, and this is mind-blowing to me, in a MOF made by Northwestern University, in a gram of that, which is about a teaspoon, if you take that and spread out the entire surface area, it has a surface area of 7,000 square meters, which is greater than a football field and a half in a simple gram. So what this does, the first and foremost exciting thing is with gas storage, and this has been applied already. In all those nooks and crannies, you can hide a lot more gas in line gas cylinders, which is how we traditionally store gas, and thus store more gas at safer pressures. You can also use it for separations, which is traditionally a very energy-intensive process. And now you can just pass a gas through a metal organic framework, and it can have a higher affinity for one gas compared to the other and get separation done that way, much more energy efficient. And finally, less related to the porosity, but still a function of these MOFs, is their catalytic properties. And when I say catalysis, think of it as doing chemistry. So it can occur at the metal sites of these MOFs, at those nodes, those metal nodes, and also at the organic struts. And Catalysis is another word we kind of have to unpack. So here is the chemistry definition. It decreases the activation energy of a reaction and consequently increases the rate of that reaction. So if we kind of make that much easier to think about, we have our starting material, this red sphere, and this hurdle, which is its activation energy, and we want it to get over that hurdle to become our product. If that hurdle's too large, it can't, and we're stuck with our starting material. If we add a catalyst, we decrease the size of that hurdle and have our transformation to the product we want much easier and actually see it happening. And a lot of materials, they come to us through some form of catalysis, but the way we're probably all most familiar with it is in our cars and vehicles in the form of catalytic converters. And catalytic converters take nasty things your car off-puts, such as unburnt hydrocarbons, carbon monoxide, and nitrous oxides, and transforms them into less harmful things, nitrogen gas, water, and carbon dioxide, by passing it over this catalyst. Now, I'm more interested in the conversion of carbon monoxide to carbon dioxide, and that's what I'm going to be focusing on. So in these catalysts, they use something called platinum group metals, which is this group here, it's seen on the periodic table right here. These are the traditionally very active catalytic metals, and kind of tend to be the best performance, and they're usually the most expensive, but there's no point in trying to compete with them because they're the best. So in this project, we're not trying to outdo and fix these platinum group metals because we can't compete. Instead, we're going to take an area where they're weak, which is at lower temperatures, below 200 degrees Celsius, where they're not as well converting this carbon monoxide to carbon dioxide. So if you imagine when you first start your car, you're going to be putting out a lot more carbon monoxide into the air until that car gets to operational temperatures, and then you'll have better conversion. So we're trying to target this weakness and create a new catalytic system to kind of be built into the traditional catalyst and fix this weakness. Why are we doing this? Because we've gotten more green conscious. We want to put less poison in the air and be better to the environment. Now, how we're going to do this is through a MOF templating process, which I'm going to get more into in a second, but you can think of it as this is a traditional catalyst, very simplified picture. Our chemistry is happening at the interface, this green box around it. If we can increase that surface area and break up this catalyst, we can have more active sites and more places for that chemistry to occur and have a more efficient catalyst. So we're going to not be using platinum group metals, but we're going to target this weakness using a different catalytic system and use this MOF templating technique to create this more efficient catalyst. Now, how we're doing this is through this MOF templating process, which is a mouthful, and I'll be saying it a lot. We're going back to our simple image of the MOF as a cube, and now every chemical and every molecule I refer to is going to be the one I actually use in my system. So these green spheres, the metal nodes, are going to be ceria or cerium oxide. These blue cylinders are the organic linking units, which are biphenyl dicarboxylate. And we can use and tune a secondary linking unit. Here I'm using bipyridine dicarboxylate, which is basically this, where we've swapped out 2 carbons for 2 nitrogens, which will give us different properties while still maintaining the same shape. The next thing that this bipyridine ligand will allow us to do is introduce a secondary metal, this copper salt, copper 2 salt, and this orange cube, as it's represented by, which can now be incorporated kind of uniformly throughout our framework. And it'll be grabbed on by those nitrogens in that bipyridine linker and kind of held in place in that MOF. From here, we're going to pyrolyze and remove all the organic units using high temperature to decompose the MOF and be left with just metal oxides. So going from this orange cube, which is the copper salt, to these kind of grayish green cubes, which are copper oxides. And we're getting a copper oxide catalyst supported on ceria. What's nice about tuning and the tunability of these MOFs is we can control how much copper is incorporated into our MOF by controlling how much of this bipyridine ligand we use, and can hopefully evenly space out that copper in some ratio that we desire. And we want to do this because previous work has shown, first and foremost, the chemistry that we're hoping for is going to occur at the interfaces of these ceria and copper oxide domains, which is right here or right here. Again, very simple representation. But previous work has shown that these catalysts perform less efficiently with large copper oxide domains. So we want to decrease the size of those copper oxide domains while balancing this interfacial area where the chemistry is actually occurring and where this carbon monoxide is being oxidized to that CO2. So what this does for us, while we decrease it, we're still maintaining a large interfacial area, as we now have, instead of 2 sites to react, 6. And we're kind of trying to balance this with this tuning and find what works best. Getting into the actual synthesis of the MOF and how we're going to achieve that, I first want to point out the naming convention I'm going to be using, which is confusing and not helpful, but it's what my mentor used and what I'm familiar with. I'm trying to make this MOF UIO67, parentheses cerium. UIO stands for University of Oslo. In the MOF community, if you make it, you get to name it, which is kind of nice. 67 refers to the 67th MOF they've synthesized and put forward. And the cerium just denotes the nodal metal, the metal kind of holding it together. And it's normally a zirconium MOF, but since we've changed it for cerium, we just wanted to note that and any future changes. Now this synthesis is the easiest I've ever done, and it's never going to get this easy again, which is a little disappointing. I used these 2 linkers that I showed earlier, the blue cylinder and the red cylinders respectively, which is the biphenyl and the bipyridine dicarboxylate. We're using that in a 2-to-1 ratio. Adding it in base, the sodium hydroxide, to deprotonate these carboxylic acids, which allows them to bind to those metals. Heating it in this organic solvent, DMF, at 100 degrees Celsius, and obtaining this viscous, milky solution, which is our linker solution, to which we're going to add cerium ammonium nitrate, which is our cerium source. And as soon as we add that, we have this bright yellow precipitate form. After an additional 15 minutes of heating, we have our desired MOF, which is UIO67 cerium. But since we've added this secondary linking unit, we now want to denote that deviation from the original MOF as well, which is why we have this BIBI 33%. It's going to be one more add-on, but that'll be it. Now we have our MOF. We just need to wash it with these organic solvents to remove anything in those large pores, remove any of the starting material, and then we dry overnight to vacate those pores and be left with a solid. It's this kind of pale yellow powder, and this is a very easy step, very repeatable, very nice. The next step, we're going to add that copper metal. So we're having that same pale yellow MOF precursor, to which we're adding this copper 2 salt, copper acetate, in excess. It's this bright blue color. We're going to dissolve that salt in DMF and mix for 2 hours with our MOF precursor and obtain our copper-doped MOF, which is great. We're going to wash it, just as we did previously, to remove any of that starting material and dry under vacuum just the same. And now we have this blue-green powder, which visually, it's what you would kind of expect to see, pale yellow. You're throwing copper in, which is this bright blue. Visually, it looks good. We've done something. The downside is to this reaction, although it's very easy to set up, very easy to run, we're getting rather low yield at less than 30%. And to some people, this might seem as a workable and usable yield, but I was scaling this reaction up from tens of milligrams to the gram scale, and this loss of product was unacceptable, both for the cost of starting materials, which although are cheap, they add up, and to the cost of my time, as I was running the synthesis repeatedly. So after trying a few things, my mentor suggested what we're seeing is actually a function of MOFs and a feature. This is work put out by Jeff Wong's group at UC Berkeley. This is a normal MOF with its representation pores being held open, and as we pull vacuum, we can compress these pores as there's nothing holding those pores open, no solvent, no gas. And this arrow going both ways shows the process is reversible. So they're able to basically expand and contract their MOF pores by using vacuum and re-added gas or solvent. What we think was happening is the same thing. We're now looking at a representation of a pore of the MOF I made. And once we pull vacuum, we don't have that reversibility. So we have our normal pore and our compressed pore. And after pulling vacuum for an extended period, we have that MOF decompose. And we're losing that structure and that rigidity. So once we're washing and adding that DMF, we're dissolving parts of our MOF and losing all of that product. To fix this, we did something rather simple, but it took a long time to get to. We made the MOF precursor, the pale yellow solid, just as we had before, washed it the same way, and then instead of pulling it under vacuum, which causes that eventual decomposition, we left it in DMF. then washed with acetone when we were going to use it and dried it for 2 hours as opposed to overnight, and that gave us a great increase in yield, which was fantastic, and allowed us to continue forward making this catalyst at a larger scale and allowed us to move to the next step, which is pyrolysis, as we go to make this active catalyst. You're heating it very hot, it's going to decompose, you're going to lose the organic units and be left with the metal bits. We're doing this in a tube furnace, which you can see here. It's a furnace that gets very hot, there's a tube running through it which is sealed to the atmosphere, and you can flow whatever gas you'd like through it and over your sample. We use nitrogen, and this is the heat ramp we used. The only really important part is this, where we're heating at 500 degrees Celsius for 2 hours. And this might seem rather hot, but it's hot enough to decompose all of those organic units. And these furnaces can easily get to 1500 degrees Celsius, so all things considering, this is rather mild. We see what looks like a burnt powder because it's basically a burnt powder. We have this black-gray powder. We burnt off all of the organic units and have just been left with those metal oxides and our active catalyst. We have about 20% mass of our starting material, which is kind of expected as we're burning off those organic units and losing a lot of that mass. This is another reason we needed to fix that earlier yield step. Otherwise, I can say this, I had to repeat this many times until we fixed it, and scaling it wasn't really feasible. From here, we need to characterize the MOFs and make sure what we're doing is repeatable, so we turn to a technique called power X-ray diffraction, where we're basically looking at the crystallinity and using X-rays to probe the crystallinity of our sample. I use this as just a fingerprinting technique. The person who was working on this project before me, Dr. Jacqueline Brandt, was a crystallographer and did a lot of the legwork for this project, so I just had to compare it to my previous work and her work to check I was repeating the synthesis properly and the work. This initial blue line is our MOF precursor. What we see is all of these nice peaks, which indicates a crystalline structure. And when we add the copper, we see the same crystallinity early on, but a suppression of the later peaks, which is fine. Maintaining the crystallinity is important here because we're trying to maintain a small copper oxide domain. And this indicates that we're maintaining that metal organic framework in that kind of even spacing once we've added the copper. So we should maintain smaller copper oxide domains and not have large ones form. And then finally, the pyrolysis looks very different because we've removed a lot of the structure to this MOF, but we still have some crystallinity and some pattern, and this is okay. What this told me was I was repeating the synthesis properly and getting the same thing every time, but it didn't tell us the actual size of the copper oxide domains, so we turned to a different technique called X-ray absorption fine structure, or XAFS, which is really fun to say. I'll be saying it a lot. So we're looking at our active catalyst sample here, and what we're going to do is shoot a high energy X-ray at the sample. It'll absorb it, and some things will happen. This is our copper, a representation of our copper energy states. So each of these horizontal black lines is a discrete energy level. It's well known and the same across copper atoms. It's occupied by electrons, these black circles. And once we shoot a high energy X-ray targeted at the specific core level, we can promote one of those core electrons out of the system, leaving us with a core hole. That's that yellow, or not yellow, white circle there. But that's not important in the scope of this explanation. Once we have this photoelectron out, it can act as both a particle and a wave, and will propagate out as a spherical wave. This red circle is a neighboring atom to one of those absorbing atoms, and this photoelectron will interact with that atom's electron density and scatter every which way, creating this interference pattern, and what we're going to use to understand the spacing between that absorbing atom and its neighbors. So that's the kind of physical side, and how we're actually measuring this is we can think of it as a simple absorption. So we have a radiation source in which we know the initial intensity very well, and we have a final intensity in our detector where we know the final thing very well. So we're using the difference between these two values to try to interpret and understand all of those cool things actually happening in the sample, which we're not actually measuring. We're looking at the difference between these two values. That's going to produce a spectra, which is going to show us absorption as a function of energy, and looks something like this, where we have X-ray absorption plotted against energy. And what we see as we slowly increase the energy, we have not a lot occurring in the absorption until we hit a certain point, and this is called the edge, where we have hit the point where that absorbing atom is going to be absorbing that energy and ejecting a photoelectron. We're going to go out and then have the absorption decrease and kind of oscillate out. So this early region is called XANES, or X-ray absorption near-edge structure. This can tell you things like oxidation state of the metal you're looking at and some other really important things. But we were less concerned with this because we knew those values for our sample, and we're more concerned with the extended X-ray absorption fine structure, which is also called XAFs and also confusing. But these XAFs and these outer oscillations can tell you, most importantly, the distance between the absorbing atoms and its neighbors, which is incredibly powerful. And I'm going to be describing how we build from this plot to the actual important data, which is going to sound rather math heavy, and maybe it is on the back end, but there's free software developed by Bruce Ravel, who is the XAFs person at Brookhaven National Lab. All of this occurs with the click of a button or two. So although it sounds like a lot, it was really easy to just click it and watch the new spectra pop up. So now I'm going to show a different plot, but it's just used to emphasize the next step. We're going to zoom in on the XAFs region, and then we're going to normalize the absorption, so it's the same across multiple spectra. We're then going to remove this background function, so we're just left with signal, and you'll probably have repeated these different experiments multiple times, and you'll average those together. To this, we're going to do our first transformation and obtain k-space data, in which we have to k-weight, which means we're multiplying that normalized absorption by some function of energy to obtain our new plot, which is a function of energy plotted against a function of energy, and this one here. This is the first actual XAFs data I'm presenting. So we're looking at this green line, which is our catalyst sample, comparing it to a copper oxide standard obtained from some chemical supplier. It's important we use a standard to compare our sample to, as the standard's going to be well indexed and can tell us about those, about the peaks and what they mean, and help us assign the peaks in our actual sample. So again, we're looking at energy plotted against energy, and this plot is not super helpful for those not well versed in XAFs. But taking us back to the physical reality and what we're seeing, these local maxima and the maximum of this plot are occurring from constructive interference, and the minima from destructive interference of that photoelectron interacting with its neighbors, creating this interference pattern. And ultimately, we're trying to understand the distance between the absorbing atoms to its neighbor. And to do that, we need to take a Fourier transform of this data to obtain R-space data. In this Fourier transform, we're taking the component sinusoidal, so sine and cosine functions, and adding them together. And we're going to be looking at a function of energy plotted against distance and obtain meaningful data. So this is that R-space data where we're still looking at our catalyst sample and comparing it to a standard. We're looking at some function of energy plotted against distance. And this distance represents the distance from the absorbing atom to its neighbors. There's two important peaks in this plot, and I want to draw your attention to the most important one, which is this copper-copper scattering distance. And what we see here for the standard is it's relatively pronounced compared to our actual catalyst sample. And what we take this to mean is in our catalyst we have a smaller copper oxide domain compared to this sample, this standard, which is good, and it means what we have done so far has been successful in this MOF templating process, and we should have a more efficient catalyst. We also have this copper oxygen scattering distance, which is prominent in both spectra. Since we have copper oxide in both of our samples, we would expect this. And looking at this, it's not the most helpful in showing the absence or presence of these copper oxide domains or of these copper-copper scattering peaks. So I'm going to present this data another way and do a wavelet transformation of this data, where we're going to take the R-space data and turn it on its side and plot it against the K-space data. And it looks kind of like a heat map or infrared. So here it is. Here is our R-space data, and we're plotting it against the K-space data, but we've taken that K-space data and are now looking top-down on it and creating this topography of peaks as we correlate these two plots. So we're still looking at our copper oxide standard and comparing it to our catalyst, and this big circle indicates those copper-copper scattering peaks and copper-copper scattering distance. which is very apparent in our standard and entirely absent in our catalyst, which again is just another way to show that we have succeeded in what we set out to do, at least to some extent in minimizing those copper oxide domains. And now we can take the next step and actually test if our catalyst is more efficient. And we're going to do this using a light-off curve, in which we're going to take whatever we're interested in modifying here, carbon monoxide, and flowing it over our catalyst, to which it'll adsorb, and then we'll get our product, this carbon dioxide. This is going to flow into a mass spectrometer, which we're just using to tell us the percent conversion from this carbon monoxide to carbon dioxide, and we're doing this and comparing it to temperature, and slowly increasing the temperature and seeing how that conversion changes. So that's the next plot I'm going to show you, which is here. So again, percent conversion plotted against temperature. And if you remember, the motivation behind all of this is to target this weak area at these lower temperatures below 200 degrees Celsius. So although we're going to 200, we want to look at temperatures lower than that. So we have three plots, this blue one, this orange one, and this green one. The blue one is a standard. It is a stoichiometric ratio of the metal oxides as we'd expect to see them occur in our catalyst. It's not MOF templated. So I took from a chemical supplier, got the both metal oxides and ground them together. And that's what we use to check and see the efficiency. And what we see is it performs much worse than these two catalyst samples. What this indicates to us is our MOF templating approach is doing something, and we're not looking at the innate reactivity of these metal oxides, which is great. This next sample is the first generation catalyst in the previous work, where it's a 1:2 copper oxide to ceria ratio, and it's MOF templated. And then we're looking at the new catalyst, which is a 1:3 ratio, also MOF templated. What we see is both of these, again, perform much better than the standard. And they're rather close in overall efficiency, but the green line is slightly better. And it's kind of hard to compare these two, so we pick a point to compare them, and we're going to look at the 50% conversion mark. And what we see is for the new catalyst, the 1:3 ratio, it occurs around 80 degrees Celsius. And in the previous catalyst, it occurs around 100 degrees Celsius. What this shows is we've succeeded in making a more efficient catalyst at these lower temperatures. But also, the much more important thing is we have been able to create a more efficient catalyst by controlling that interfacial area and that copper oxide domain. And the really cool thing I think about this work is we've created a catalyst with less copper in it compared to the previous catalyst and have higher efficiency even though we have less of that active metal, just by controlling that domain size and that interfacial area. So to wrap this up, in this process and in this work, was able to improve the synthesis of this catalyst, was able to scale it up from the tens of milligram scale to the gram scale, where it could actually be tested for these catalytic efficiencies, and improve the step with low yield. In our XFs data, we saw the absence of this copper-copper scattering peak, which indicates we succeeded in minimizing the size of the copper oxide domain in our catalyst, which should mean an improved efficiency, which is what we saw. And again, improved efficiency despite less copper in the sample. So what this means for the future, the next baby step, as the work I was doing was just a baby step from the previous work, is doing the same chemistry and that same MOF templating approach, but using a third metal, which here would be cobalt. Before I left Oak Ridge, I synthesized the preliminary catalyst for this and collected powder patterns, but no further work had been done. And the pie in the sky goal and the ultimate hope for this work is to create platinum group metal catalysts, those really efficient ones I mentioned earlier, create those more efficiently using this MOF templating approach. And again, the chemistry we're seeing is occurring at the surface interface of these catalysts. So we want to take the traditional catalyst and the traditional way to make these catalysts and create smaller nano domains through this MOF templating to give us more active sites and ultimately improve the atom economy of these reactions and of these catalysts and use less metal but get a higher efficiency, which would be fantastic. But we're currently right here, and I'm very excited to see where this goes in the future. I have a lot of people I'd like to thank. my mentor at Oak Ridge, Dr. Carter Abney, who was fantastic to work with, Dr. Jacqueline Brandt, who I said did a lot of the legwork for this project. Dr. Matt Curley was a postdoc, and Philip Haustenberg was a post-bachelor in the lab I worked in and helped me kind of orient myself and were great to work with. Dr. Felipe Garzon was in the Catalyst group next to us and collected the light-off curve data I showed you. That wouldn't have been possible without him. Dr. Dave Mullins was also in that Catalyst group and allowed us to use his beam time to collect that XFs data because the first time we tried, our samples were too concentrated. I'd like to thank Allison, who was the resident director for the program I was at while at Oak Ridge, and also my advisor here, and it's just fantastic. And I appreciate her listening to my talk and giving so much feedback. The same goes to Graham and Dr. Dave. And I'd also like to thank Daniel, because over the years I've badgered him so many times, and a lot of the things I've done at Lawrence wouldn't be possible without him. All the chemistry seniors for listening to my talk and giving feedback, and finally ORISE in the Department of Energy for funding, and Nanomaterials Chemistry Group for giving me a place and the opportunity to do this chemistry. Thank you all for listening. If you have any questions. Gus?
The heat map data,
Yeah.
so for that one, my question is, why is the COP the same on your standard and, like, it seems like it's the same intensity, but you're saying that the copper interfaces are not, they're not as close together, and that's why you're not seeing that, yeah?
Yeah, so it's, in this sample, we're looking at basically the crystal size of that copper oxide. And what will often happen is we'll form large crystals, which is what is decreasing the efficiency of this reaction. So we're still forming those crystals, we're just trying to make them as small as possible. So we're still seeing the crystalline structure of this, and the copper oxygen scattering distance is going to be the same in that crystal. We're just trying to make it small enough that we don't have that copper-copper distance.
I see, so it's just about distances between things, not about the presence of them or not.
Yeah, it's maintaining size. Graham?
Do you ever see anything with copper cerium distance, or are you not within the range of that ionic radius?
Yeah, so the energy levels to look at these metals vary dramatically. And I know for cerium we can't look, so we're using the K edge for the copper, and you have to use a different edge for the cerium. And this is all being kind of predicated by the previous XFs results from the last catalyst, which they didn't collect cerium data for. I think the issue with that is looking at kind of overlap of edges and getting really messy, hard to interpret data. I don't know if that's possible either, but it might be.
You wouldn't see it scatter off the ceria either?
It might be in, it could be happening here, which are multi-scattering peaks, and very hard to index without modeling first, and this is preliminary data, so that hadn't been done. Deanna?
Can you go back one more? So with this one, although as you go longer on, all those peaks that you're seeing in your standard that you're not seeing in your copper, is that structure that you're seeing that makes it look just the red line look a little noisier than the green line? Is that wet copper structure is coming for them eventually?
So I'm not sure. I don't know how to read K-space data.
So my note at first was just, why is the standard noisier here?
So as you go further out, further in the energy range, you're going to get a lot more noise, and it's harder to interpret. This is only good to about 6 angstroms, and although you can collect much further, that data is not reliable.
But it's the relative that I'm curious about.
Between these two?
Yeah, so it looks, you get the relative, the noise is different. Thank you.
Couldn't tell you, yeah. Eli?
What's maybe this is because I haven't done chemistry in a very, very, very long time, but what's K space and what's R space?
That's a great question. So that's how they kind of describe these two plots. And in K space, we're in energy space. I'm not sure why it's called K space. And R space data is this distance space. So it's just distinguishing these two plots and these two kind of, these two types of data. Allison?
K represents momentum. Anyway, so totally right. But it's the German, I think, for moment. I can't remember exactly what they say K. But question. So what the pyrolysis gets rid of the which bit does it get rid of?
The organic linking units.
Cool. So what sort of temperature stability do you have in terms of structure? Because the catalysis ability changes with temperature, but does it morph around when you go into these low temperature, high temperatures?
So that's a great question. And once we have pyrolyzed it and removed those organic linking units, our metal oxide should be really stable at whatever temperature we're looking at. If we do anything with the MOFs themselves at those temperatures, we will see that fluctuation.
Okay. But that's pre the pyrolysis or pyrolysis.
Yeah.
Okay.
Leo?
All the stuff about XF seems really interesting, but really complicated. Do you have any suggestions of like resources if I wanted to learn more about it?
Yeah. It is a fantastic resource. It's called XF for Everyone by Scott Calvin. I'm plugging this. This has been like everything I've used to try to piece anything together about XFs. It's great. There's running dialogue by cartoon animals, kind of explaining the science. Deanna?
So in the MS experiment where you're running CO and seeing the conversion, A, what is your carrier gas? B, how much CO is in that stream?
It's 2% carbon monoxide, and the carrier gas is purified air. And we were just trying to model it at the actual, what we would see out the tailpipe. Eli?
How long does it take for the car to like that heat range? Like,
That's a good question. I'm not sure. The source I was kind of pointed to didn't give any more details, and I'm sure there's plenty of sources out there. I imagine it's only a couple minutes.
okay.
Stefan?
I know you're not looking at this right now, but when do you start worrying about like follow-up, trying to introduce, okay, is the other things that are going to come through the tailpipe going to run the system?
Yeah, so there was some really cool chemistry done trying to make these kind of platinum nanoparticles to combat this very thing, and they get, I'm trying to think of the word, they face problems with all the other stuff. So that is a great question, and the other work that's been done on this has run into that problem. And I imagine probably further down the line after we do the next step, which is adding that ternary catalyst and seeing, okay, this is a known system, we know it improves better than the previous system, now let's test actually how good it is outside of this basic system. Gus?
Do you need longer organic linkers to add another metal for the ternary system or not? Same size?
So for this system, this is super preliminary, and my mentor kind of shrugged and said, see if it works. But again, we only care about binding those through that bipyridine ligand. So it doesn't really matter the length of that, at least for this system, and we're just trying to use that to control how much we can incorporate. Nikki?
Could you go to your catalytic efficiency slide? I think it was towards the end. So just to clarify, the blue and the green, you said those were the same mixtures, but you made the green happen by just changing like the size of the crystal?
So the green is the catalyst sample where we're trying to control that crystallinity and the size of that copper oxide domain.
Okay.
And the blue one is just taking those two known metal oxides and throwing them together.
Have you thought about manipulating the 1-2 ratio?
Yeah, so the previous work was much more thorough and went through a bunch of different testing ranges. And what they found is there was some competition between mechanisms at a certain point. So this 33% was picked to try to kind of mediate and pick the one more efficient mechanism.
Other question? Let's thank the speaker then.